So far in this course, we have learned several ways to solve some particular types of differential equations. Unfortunately, most often you have to resort to estimations to solve most differential equations out in the real world. So at that point, the question becomes, when do we know that a particular differential equation, and in particular an initial value problem, when do we know when that has a solution? Well, in this section, we're going to discuss the existence and uniqueness theorem. So when these certain conditions occur, we will not only know that the particular differential equation will have a solution, but we will also know that it is the only solution. And so that's first thing to say is that we define a first order initial value problem to look like this statement up here. So we rewrite the differential equation as dx dt is equal to f of t of x. And we're given some initial value, x of t naught is equal to x naught. Okay. So the existence and uniqueness theorem. We define some rectangular region R, where along the t-axis it goes from A to B, and along the x-axis it goes from C to D. So that's some rectangular region that contains the initial value t naught comma x naught. If on that region R, both f of t of x and the partial of f with respect to x are continuous on that entire region, then the first order initial value problem has a unique solution in some interval containing t naught. So again, what does that say? It says not only will we have a solution, but that solution will be unique. Make a quick note that if theorem 1.2.1, so if this theorem that we just talked about is not satisfied, then we'll just say that the answer is inconclusive, or in other words, that the theorem doesn't actually give us any information. It may turn out that if those conditions are don't occur, it's possible that we will still have a solution, but it may not be unique. There may be several solutions to the initial value problem. So let's go ahead and take a look at this doing a few examples. Okay. So let's start with the initial value problem. T times x prime is equal to x, and we're given that x of a is equal to b. We want to find the values of a and b such that the following initial value problem has a unique solution. So what do we want to do? Well, let's rewrite the problem as x prime is equal to x over t. And this will tell us that f of t comma x is equal to x over t. So that's our function f of t comma x. Now, our theorem says that if that is continuous on some region R and the partial derivative of f with respect to x is continuous on some rectangular region R that contains an initial value, then we have a unique solution to that initial value problem. So where is f of t of x continuous? Well, it is continuous everywhere except t equal to 0. All right, and what about the partial derivative of f with respect to x? Well, the partial derivative of f with respect to x is just 1 over t. And so write that down. Partial derivative of f with respect to x is 1 over t. So this is also continuous everywhere except for t equal to 0. So then the question is, all right, so when will we have a unique solution? Well, that would be every point as long as t is not equal to 0. If t is not equal to 0, no matter how close it is to 0, we can find a rectangular region, no matter how small it needs to be, that does surround the point so that the function is continuous and its derivative with respect to x is continuous. So this actually tells us that there is a unique solution as long as t, which is a in this problem, as long as a does not equal 0. All right. We could actually solve this problem and see what happens with those values a and b. So we're going to solve this problem using methods that we've learned previously and see that this why this might make sense, why this solution might make sense. But that's actually it. This is the end of the problem. We're just going to do a little bit more work on it to get a little bit more of an idea of why this worked out in this way. All right. So let's solve this initial value problem. We can rewrite this as the linear equation x prime minus 1 over tx is equal to 0. This tells us that we have the integral of 1 over t dt is equal to negative ln of t. And so the integrating factor is e raised to the negative ln of t, which is t to the negative 1. So this is the left-hand side becomes ddt of t to the negative 1 times x is equal to 0. We integrate both sides, and this is t to the negative 1 times x is equal to some constant c. And we were given that x is b and t is a. So this actually tells us that we have b over a is equal to c. Just filling in what t and x were here. So we have b over a is equal to c, and this is our solution to the initial value problem. So if we rewrite all of that, that is x is equal to t times c, but c was b over a. So here is our initial value, the solution to our initial value problem. Notice that if we do plug this in, right, we'd have the x is t times c, or b over a times c. B over a times t. And then the derivative, x prime, then is just b over a. But if we multiply that by t, we get back to what x was. So that does, in fact, solve that differential equation. And moreover, we notice that this should be true as long as a does not equal 0. So that actually fits with what we had said earlier. And again, there will be a unique solution. And moreover, this theorem above tells us that this is the solution, but also this is a unique solution. So there are no other solutions. All right, really quickly, we're going to do a couple more examples, but these will be fast. Okay. We're going to determine whether the existence and uniqueness theorem guarantees a unique solution to the following initial value problems. what we want to do is we want to write it in terms of x prime is equal to some function of t and x. So this is x prime is equal to negative 2tx to the 1/3 power. We notice that f of t comma x is continuous everywhere. And then we need to take the partial of f with respect to x. So this is negative 2t times 1/3 x to the negative 2/3. Or in other words, negative 2t all over 3 times the cube root of x squared. And this is continuous as long as x does not equal 0. So if we have any initial values that as long as x is not equal to 0, we will be able to find a rectangular region in which both f and the partial of f with respect to x are continuous and contain that point. So this first one up here, this existence and uniqueness theorem guarantees that this first equation does have a unique solution to this, does have a unique solution because x here is -1. So, which means it's not 0, right? So this does have a unique solution. Unfortunately, this does not have a unique solution, or at least we'll say that the theorem is inconclusive for the second one here because x is equal to 0, so we cannot find a region around a rectangular region around that point that is continuous for both f and the partial of f with respect to x. And that is it for that problem. Now let's have a quick talk about what this inconclusive means, though. Really, we're just saying that the theorem gives us no information. It may still turn out to be true that there is just a unique solution, that there is a solution and it is unique, but it's completely possible that there's not a solution or that there are many solutions, but not just one. We don't know. Or at the very least, that theorem doesn't tell us. And we'll have to use other methods to try to determine. Okay, one last example here. So again, we want to rewrite it. And this is continuous as long as x does not equal. Continuous as long as x does not equal 3. Actually, I should say x is greater than 3. We're not going to discuss the endpoints, right? If x is equal to 3, that is allowed, but we can't find a rectangular region around x equal any point that x is equal to 3, because that would move over into values of x that are less than 3, which we are not allowed here in this problem. So if we're going to satisfy our existence and uniqueness theorem, we need x to be greater than 3. Let's go ahead and take the partial of f with respect to x just to check that. And we get t times, this should be 1/2 times x minus 3 to the negative 1/2. So again, we get that it is continuous as long as x is greater than 3. And well, that's it then. Because if we look at this first part up here, this first one, we have t is 4, x is 3. So our existence and uniqueness theorem doesn't say anything because, again, we cannot find a rectangular region R around the point 4, 3 that is continuous, that F is continuous on. So this one is inconclusive. But the second one has a unique solution. So we'll write has a unique solution. And I'm running out of room there, so I'm going to abbreviate that. Okay. So that second one, again, has a unique solution. And that's it. So that is it for this video.